Good morning. This is day 8 of the Precalculus review, and today we need to talk about graphs of trigonometric functions. And before we do that, just real quickly, let's review some of the angles that we have memorized on the unit circle and their corresponding ordered pairs. An angle of 0 radians corresponds to the positive x-axis on the unit circle. The radius there is 1. So the ordered pair that corresponds to an angle of 0 radians is 1, 0. 1 because we're at 1 on the x-axis, 0 because we haven't gone up or down. The ordered pair which corresponds to an angle of measure pi over 2 radians is the ordered pair 0, 1. The ordered pair which corresponds to an angle of pi radians is the ordered pair -1, 0. And the ordered pair that corresponds to an angle of measure 3/2 pi radians is the ordered pair 0, -1. This is going to be helpful to us as we graph, because when I say what is sine of 0, I'm asking you for the y-coordinate of the ordered pair that corresponds to an angle of radian measure 0. And when I say, for example, what is cosine of pi, I'm asking you for the x-coordinate of the ordered pair that corresponds to the angle of pi radians. So as we're graphing these trigonometric functions, on one hand I have one handout that I gave you, I have the basic functions, and then I have on another handout some examples of these functions when they've been shifted left or right, compressed, maybe reflected with respect to the x-axis and so on. But when we graph these trigonometric functions, I want to make sure that you're aware that the ordered pairs we're graphing, x, y, x stands for the radian measure of an angle, and y is going to stand for the trig value of that angle. Now it could be sine or cosine or tangent, but x is going to be the measure of the angle, y is going to be the trig value of the angle that has a radian measure of x. To graph y equals sine of x, let's make a let's make a xy chart, and just remember that x is radians and y is going to be the sine of x, or the y-coordinate of that ordered pair at x radians. If we start with 0 radians, we can look at our graph here and say at 0 radians, sine is 0. So the graph of y equals sine x is going to go through the ordered pair 0, 0. And at pi over 2 radians, the sine of pi over 2 is the y-coordinate of that ordered pair. It's 1. So our graph is going to go through the ordered pair pi over 2, 1. At pi radians, sine of pi radians is the y-coordinate at pi radians. That's 0. And 3/2 pi, at 3/2 pi, sine of 3/2 pi is -1 because that's the y-coordinate. And at 2 pi, we're back to 0 radians, and sine of 0 is 0. So our ordered pair is going to go through, our graph is going to go through the ordered pair 2 pi 0. Now let's just graph these 5 points and see what the graph looks like so far. It's going to go through the ordered pair 0, 0, the ordered pair pi over 2, 1, the ordered pair pi 0, the ordered pair 3/2 pi -1, and the ordered pair 2 pi back to 0. If I connect those points in a nice smooth graph, then I have what's called one period of the graph of the function y equals sine x. This is one period of the graph. Now, of course, we could go around the circle in a clockwise direction and find the sine of lots of negative angles if we wanted to. We could go backwards to negative pi over 2. Negative pi over 2 would be the same as 3/2 pi. Sine would be -1. So at negative pi over 2, the value of the function would be -1. At negative pi, the graph of y equals sine x would be back to 0. So this graph is called a cyclical function because it repeats. But really, what we're practicing today is just graphing one period of each function. So when I say graph one period of y equals sine x, you can just graph that function from 0 to 2 pi. Really, I have endpoints and midpoint here. Of course, y equals sine x doesn't have endpoints because it goes forever to the left and forever to the right. But when I say endpoints, I'm talking about the endpoints of one period of that graph. So for the endpoints of sine, I'd have 0, 0, and 2 pi, 0. And for the midpoint of that graph, halfway between 0 and 2 pi radians is 1 pi radians. And I see at 1 pi radians, sine is also 0. So those are really the x-intercepts of the graph of y equals sine x. 0, 0, pi 0, and 2 pi 0. Now in just a minute, when we get to graphs that have been shifted left or right, we're going to find these endpoints and midpoint by taking the argument of the function that we're graphing. If we're graphing y equals sine of bx plus c, we're going to take that bx plus c and set it between the normal endpoints for one period of sine. We'd set the bx plus c between 0 and 2 pi, and then solve for x. That will give us our new endpoints and our new midpoint to show us how the graph has been shifted. All right, let's go ahead and finish these simplest graphs before we start shifting and rotating. Second, I have y equals cosine of x. And on our xy chart, we can use the same radian measures. We can use 0 and pi over 2 and pi and 3/2 pi and 2 pi. For our y values, we want the cosine of each one of those angles. So we want cosine of 0. That means we want the x-coordinate of the ordered pair that corresponds to an angle of 0 radians. The x-coordinate is 1. So at x equals 0 radians, cosine is 1. At x equals pi over 2 radians, cosine is 0. At pi radians, cosine is -1. I'm just peeling off the x-coordinates of these ordered pairs. At 3/2 pi, cosine is 0 again. And at 2 pi, we're back to where cosine is 1. The x-coordinate of 2 pi radians is 1. So let's graph those 5 ordered pairs. 0, 1, pi over 2, 0, pi -1, 3/2 pi 0, and 2 pi, we're back to 1. And again, this graph is cyclical, so whatever it does to the right of the y-axis, it's going to do the mirror image of that to the left of x-axis, the y-axis. If we go to -pi over 2, cosine is back to 0. And if we go to -pi, cosine is back to -1. If I connect those dots with a nice smooth curve, I have the graph, or part of the graph, of cosine. But what you're going to need to do in tonight's homework is just graph one period of the function. So one period of the function of y equals cosine x, we're going to say this is one period where the graph does its whole thing from 1 to -1 back to 1. And we're going to call the endpoints of that one period, the order pair 0, 1 is this left endpoint. The ordered pair 2 pi 1 is this right endpoint. And the ordered pair pi -1 is the midpoint of the graph of one period of the function y equals cosine x. So when, in a minute, when we have a graph that has been shifted, we're just going to take the argument when we're graphing y equals cosine of bx plus c. We're going to take the bx plus c and set it between the normal endpoints for one period of the graph, 0 and 2 pi. And we'll solve for x, and that'll give us the new endpoints. To graph y equals tangent x, I need to think of tangent as being sine over cosine. So for each ordered pair, I need to take the y value and divide it by the x. Now, what do you know about the value of a fraction where its denominator is 0? Wherever the denominator of a fraction is 0, that function is undefined. So in this case, for the graph of tangent x, wherever cosine is 0, the graph is undefined. The function is undefined. And what does that mean about the graph? What is the graph of a rational function? This is a rational function. What happens to the graph of a rational function where its denominator is 0? Where the function is undefined, where the denominator is 0, there are vertical asymptotes. You can't let x be anything that would make cosine 0, so you have to put vertical asymptotes there. Cosine is 0 at the half pies. We can see right here cosine is 0 at pi over 2 and at 3/2 pi. So on the graph of tangent, that's where we're going to have vertical asymptotes at all the half pies, including, if we want to go backwards, we graph a vertical asymptote at -pi over 2. When we look at the midpoint between two vertical asymptotes, say when x equals 0 radians, at 0 radians, what's tangent? Well, at 0 radians, tangent is the y divided by the x. The 0 divided by 1 is 0. So the graph of tangent is going to go through the ordered pair 0, 0. And what about at pi radians? At pi radians, tangent would be the y divided by the x. The 0 divided by -1 is 0 as well. And at 2 pi radians, so, and at -pi radians. At all the half pies, tangent has vertical asymptotes, and at all the whole pies, tangent has x-intercepts. And if we think about what the graph looks like then on either side of the x-intercept, think about this. From -pi over 2 to 0, this interval from here to here, on the unit circle, that is the fourth quadrant. -pi over 2 is the same as 3/2 pi, and from -pi over 2 to 0, would tangent be positive or negative? In the fourth quadrant, the x's are positive, the y's are negative, so all of the values of tangent are going to be a negative divided by a positive. All the values of tangent between -pi over 2 and 0 are going to be negative. That means this piece of the graph from -pi over 2 to 0 is below the x-axis. And that's part of the graph of one period of tangent. But what about from 0 to pi over 2? What quadrant is that on the unit circle? From 0 to pi over 2, from 0 to pi over 2 is the first quadrant where both the x and the y are positive. So all the values of tangent are positive. A positive divided by positive is a positive. So from 0 to pi over 2 on the unit circle, or from 0 to pi over 2 on this graph, the values of tangent are positive. Where have you seen a graph that's that basic shape before? What does that look like? Well, if you think about your polynomial functions, y equals x cubed is that snake-shaped graph that goes through the origin and is increasing from left to right. So the graph of tangent kind of looks like the graph of y equals x cubed between its asymptotes. I am not by any means saying that it is the same graph. I'm just saying when you need a mental image of tangent x, you can think, hey, that looks pretty much like x cubed between its asymptotes, and the asymptotes are at the half pi's because that's where cosine is 0, and we can't let cosine be 0 because that makes the function undefined. So the same thing would happen from pi over 2 to pi. From pi over 2 to pi, that's the second quadrant, tangent would be negative. And then from pi to 3/2 pi, tangent would be positive again. So this function is repeating. It's a cyclical function like sine x and cosine x in that it keeps repeating. But if I ask you to graph one period of the function, it's the interval over which the graph does its whole thing. This graph does its whole thing in just a distance of pi radians. From negative pi over 2 to positive pi over 2, that's just 1 pi radians. From pi over 2 to 3/2 pi, that's just 1 pi radians. So in just a minute, I'll go ahead and make a note here, but we're going to say the period of tangent x is pi radians, where the period of sine and cosine was 2 pi radians. It took 2 pi radians for sine and cosine to do their whole thing. It only took 1 pi radian for tangent to do its whole thing. And when we graph functions of tangent that have been shifted, we're just going to take the argument of that function and set it between the normal left and right asymptotes that we use for one period of the graph. We're going to set the argument between negative pi over 2 and positive pi over 2, solve for x. That will tell us where our asymptotes have been moved. That'll make sense and just make a little more sense in just a minute when we do some graphs that have been shifted. But we're going to use one period of tangent is from negative pi over 2 to positive pi over 2. The graph of cosecant. Cosecant is the reciprocal of sine. So this graph is going to have its vertical asymptotes wherever sine is 0. And if we look at the graph of sine, it's 0 at all the whole pi's. So cosecant is going to have its asymptotes at the whole pi's, including 0. It's kind of hard to dash in the y-axis, but that's one of the vertical asymptotes along with negative pi, positive pi, and 2 pi. All right, let's think about what this graph looks like. It's going to have vertical asymptotes at the whole pi's. What's going to happen at the half pi's? What is cosecant at pi over 2? At pi over 2, sine is 1, so cosecant's the reciprocal of 1. The reciprocal of 1 is still 1. So at pi over 2, cosecant is 1. What about at 3/2 pi? At 3/2 pi, the ordered pair is 0, negative 1, so sine is negative 1. Cosecant would be the reciprocal of negative 1. That's still negative 1. So far we have the vertical asymptotes. We have at the half pies, it looks like we're bouncing back and forth between positive 1 and negative 1. What about from 0 to this half pi? From 0 to half pi, that is the first quadrant from here to here. What's the sign, S-I-G-N, of cosecant in the first quadrant? Well, the reciprocal of a positive is going to be a positive. So between 0 and pi over 2, this graph is going to go up. And between pi over 2 and pi, between pi over 2 and pi, sine is positive, so cosecant is going to be positive. The graph goes up again. And then from pi to 2 pi, I think all the way from here to here, what can you tell me about the value of cosecant in the third and fourth quadrants? No, in the third and fourth quadrants, sine is negative, so cosecant is negative. In other words, this part of the graph goes down. Now, there's a lot more we could say. I'm not giving you the complete lecture on graphs of trig functions, but I'm just trying to get the basic shape of these 6 graphs. And for cosecant, I can think it has vertical asymptotes at the whole pies, because that's where sine is 0, that's where cosecant's undefined. I can find the value of cosecant pi over 2 is positive 1, cosecant of 3/2 pi is negative 1, and then I can just remember that between 0 and pi, cosecant is going to be positive. Between pi and 2 pi, cosecant is going to be negative. So this ends up looking like a pair of parabolas. Now, it's not a parabola, but if we're trying to get a mental image, we can think this is going to look like a pair of parabola. And what would you say is the amplitude of this, not amplitude, I'm sorry, the period of this function? How wide of an interval does it take for the graph to do its whole thing? Well, whole thing would be a concave up looking U-shape and a concave down looking U-shape. So it takes a period of 2 pi for cosecant to do its whole thing. Just like sine x, the period of cosecant x is 2 pi. It has left and right asymptotes at the whole pies. Let's say at 0 is, for one period of the function, I'm going to say one period. It's going to have a left asymptote at 0 and a right asymptote at 2 pi and a middle asymptote at 1 pi. So for any other graph of cosecant that's been shifted, I'm just going to take the argument of the function, whatever it is, and set it between these normal left and right asymptotes, 0 and 2 pi, solve for x. That will tell me where the graph has been shifted to. Secant x is 1 over cosine x. So it's going to have its vertical asymptotes wherever cosine is 0, and cosine is 0 at the half pies. Negative pi over 2, at pi over 2, at 3/2 pi. I bet if we have a left and right asymptote and a middle asymptote, we'll get one whole period of secant. Let's see if we get a concave up and a concave down for secant, just like we did for cosecant. What about from negative pi over 2 to positive pi? Well, let me back up 1 second. What about at 0? What's the value of secant x at 0? Well, at 0 radians, x is 1, so cosecant would be 1. At 0 radians, cosecant is 1. pi radians, cosecant, I'm sorry, I keep saying cosecant when I mean secant. At 0, secant of 0 is 1. At pi radians, secant of pi radians is negative 1. And then from negative pi over 2 to positive pi over 2, this is negative pi over 2 to positive pi over 2. That's where all of your x's are positive. So all of your secants are positive. That means between this left and middle vertical asymptote, we have our concave up U shape. And from pi over 2 to 3/2 pi, here's pi over 2 to 3/2 pi. That's where all of our x's are negative. So all of our secants are negative. And that's where we have the concave down piece of the graph. This is one period of secant from negative pi over 2 to 3/2 pi. So when we have a graph that's been shifted, we're going to take the argument and set it between this normal left and right asymptotes. Normally we're going to say the left and right asymptotes are negative pi over 2 to 3/2 pi, with the middle asymptote being at 1/2 pi. And then we can set the argument of a graph of secant that's been shifted between that left and right asymptotes to see where they've been moved to. All right, last one, cotangent, and then we'll have our 6 basic graphs. Cotangent is cosine x over sine x. So it's going to have its vertical asymptotes wherever sine is 0. We can look back at the graph of sine and see that it's 0 at the whole pi's. So that's where cotangent is going to have its asymptotes at the whole pi's. Here's 0 radians, 0 pi. Here's 1 pi. Here's 2 pi. I could go back to negative pi if I wanted to. But it has the asymptotes at the 1/2 pi's. And what happens between the asymptotes? What happens to cotangent at the, I wrote the wrong thing. I said cotangent has vertical asymptotes wherever sine is 0. Sine is 0 at the whole pi's. So I graphed these asymptotes correctly. I just wrote the wrong thing here. It has its asymptotes at the whole pi's. And halfway between the whole pi's, at the 1/2 pi's, what's cotangent? Pi over 2. Cotangent would be 0 divided by positive 1, which is 0. At 3/2 pi, cotangent would be 0 divided by negative 1, which is 0. So cotangent has its x-intercepts at the 1/2 pi's. And just because we need to pick up speed a little bit, and you've seen this before, I'm going to tell you that cotangent looks like the graph of tangent reflected with respect to the x-axis. And that makes sense because these two functions are just reciprocals of each other. The graph's reflected with respect to the x-axis. So where tangent x looks like positive x cubed, cotangent x looks like negative x cubed. But if we only want to do one period of that graph, we're going to say one period of the graph of cotangent lies between the vertical asymptotes at 0 and at pi. So when we want to graph cotangent that's been shifted, we're going to set that argument between the normal asymptotes, 0 and pi. solve for x. That will tell us where the graph has been shifted. All right. You have this page in the packet that I gave you, and we're going to graph some functions that have been shifted. This is just kind of a recap of what we just figured out, except for I've thrown in one new word there. We mentioned the word period, the length of the interval that it takes for the graph to do its whole thing. What about amplitude? The amplitude of the graph, number one, amplitude really only applies to sine and cosine. It's the height of the graph, how far the graph goes above the x-axis or how far the graph goes below the x-axis. The graph of sine x has an amplitude of 1 because the graph goes 1 above the x-axis and it also goes 1 below the x-axis. The graph of cosine also has an amplitude of 1. It goes 1 above the x-axis to 1 above the below x-axis. So it's just the height of the graph relative to, well, if the graph hasn't been shifted, it's relative to the x-axis. Let me leave that comment unfinished and say the amplitude of the graph comes from the coefficient of sine or cosine. Now, because amplitude is a distance, it can't be negative. So if a happens to be a negative number, we say the amplitude is the absolute value of a. In this example, y equals 2 sine of x minus 2/3 pi. 2 gives us the amplitude of the graph. And we know that this graph is going to rise up 2 units above the x-axis and 2 units down below the x-axis. The period of a function is just its normal period divided by the coefficient of x. The normal period for sine, we said it's 2 pi. So the period of this graph is 2 pi divided by the coefficient of x, whatever it is. And so for our example, the normal period for sine is 2 pi divided by that coefficient of x is just 1. So this graph is still going to have a period of 2 pi. This x minus 2/3 pi, that is shifting the graph horizontally. If you think about from algebra, when we graph x squared, and then we graph x minus 7 squared, we say that 7 is a horizontal shift, and the horizontal shift always works the opposite of what we expect. Subtracting 7 before we square the x actually shifts the graph 7 to the right. Here, we have the graph of sine shifted 2/3 pi units to the right. But I am really bad at picking up this whole graph and shifting it 2/3 pi units to the right, and that's why I gave you this hint. If you're looking for where the new endpoints and midpoints of your function are, you just set the argument between the normal endpoints for sine. In this example, we could get one cycle of the graph or one period of the graph by setting x minus 2/3 pi between 0 and 2 pi and solve for x. That's a compound inequality. You have to add 2/3 pi to all 3 sides. 0 plus 2/3 pi is 2/3 pi. And 2 pi is 6/3 plus 2 more thirds is 8/3 pi. And the other thing you can remember from your graph of sine is at its endpoints, sine is 0. So here, at the endpoints, 2/3 pi and 8/3 pi, this graph will have a value of 0 as well. You could put 2/3 pi in place of x 2/3 pi minus 2/3 pi is 0. Sine of 0 is 0. And 2 times 0 is 0. So that's still the y value of those two endpoints. Now, because my endpoints, or in my endpoints, my radian measures are multiples of 1/3, I want to count by 1/3 pi on my graph. I don't want to count by pi over 2's when the endpoint of this graph is at pi over 3's. So I'm going to label the first tick mark, here's 1/3 pi, and then 2/3 pi, 3/3, 4/3, 5/3, 6/3, 7/3, over here is 8/3 pi. From 2/3 pi to 8/3 pi, I should have one complete period of this graph. And we've determined that at its endpoints, 2/3 pi and 8/3 pi, this function is going to have a value of 0. And at its midpoint, it will also have a value of 0. So the midpoint between 2/3 pi and 8/3 pi is 2/3, 3/3, 4/3, 5/3. That's where this function has its x-intercepts. And then very quickly, if you have this image in your head, you can think between the left endpoint and the midpoint, sine is going up to 1. Between pi and 2 pi, sine is going down to -1. That's still the general shape of this graph, only because of the amplitude change, rather than the graph hitting the high point at +1 and the low point at -1, it's going to hit halfway between 2/3 pi and 5/3 pi. It's going to go up to 2 instead of 1. Halfway between 5/3 pi and 8/3 pi, the graph is going to go down to -2 instead of -1. So this is one period of that graph. And we are going to be using graphing calculators in calculus, but if you don't have a quick mental image of what the graph should look like before you graph it on your calculator, that would be like someone who didn't know their multiplication tables and they hit 5 times 7 and the calculator said 12. You don't just write that down as the answer to 5 times 7. You know that 5 times 7 is not 12. So you go back and you find your mistake. The same way with graphing calculators. If you don't have a quick mental image of what that graph is supposed to look like and you think you've typed it correctly on the calculator and you graph it and you don't know what to expect, you'll copy down any old graph the calculator gives you without realizing that you've made a mistake. All right, let's look at the second graph. Like sine, the amplitude of this function is given by the coefficient of the function. Coefficient of this function is 5. So instead of hitting a high point of +5 and a low point of -5, instead of hitting a high point of 1 and a low point of -1, this graph is going to hit a high point of 5 and a low point of -5. And to find one cycle of the graph, I just need to set the argument 2x plus pi over 2 between the normal endpoints for one cycle of cosine. And one period of cosine, we said it has its endpoints at 0 and 2 pi. So we're going to set that argument between 0 and 2 pi. One other thing I forgot to mention right here, the period of the graph is always the normal period of cosine, which is 2 pi, divided by the coefficient of x. Coefficient of x is 2, and 2 pi divided by 2 is just pi. So this graph is going to do its whole thing in an interval of just pi radians rather than taking a full 2 pi radians. All right, let's solve that inequality by solving for x. We'd have to subtract pi over 2 from both sides. Actually, all 3 sides of the inequality. That's 4 halves minus 1 half is 3 halves pi. And then we'd have to divide all 3 sides by 2. Negative pi over 2 divided by 2 is negative pi over 4. 3 halves pi divided by 2 is 3/4 pi. Now, notice we said the period of this function should be pi. Is that the actual distance we have between the endpoints from negative pi over 4 to 3/4 pi? Is that 1 whole pi radians? Yeah, 3/4 minus negative 1/4 is 4/4, 4 pi radians. So the endpoint for one period of this function are going to be at negative pi over 4 and 3/4 pi. And we just need to say, what is cosine, what's normally the value of cosine at its endpoints? Well, on the interval from 0 to 2 pi, at its endpoints, the y value is 1. Instead of hitting positive 1 and negative 1, we said at its endpoint, this is going to hit positive 5, well, excuse me, from 0 to 2 pi, the graph is hitting positive 1 at both endpoints and negative 1 at the midpoint. So this is going to hit positive 5 at both endpoints and negative 5 halfway between those 2 endpoints. I really haven't left myself enough room to write here. Let me, since my endpoints are quarter pies, that's what I'm going to make my tick marks represent on the x-axis. And x is negative pi over 4. Y is 5. And when x is 3/4 pi, y is 5. Halfway between negative pi over 4 and 3/4 pi, the value of this function is going to be negative 5. Halfway between negative pi over 4 and 3/4 pi is positive pi over 4. That's where the graph hits negative 5. So one period of this function looks a whole lot like the graph of cosine, except for it's been shifted pi over 2 units to the left, and the period has been condensed to only 1 pi instead of 2 pi, but it's still this U-shaped graph that cosine gives us in one period. All right. Number 3, tangent x. We said tangent is sine over cosine, so it has vertical asymptotes at the half pi's, negative pi over 2, positive pi over 2, 3/2 pi, and so on, because that's where cosine is 0. And we said the normal period for tangent is 1 pi. So if we have a graph that's been shifted or compressed somehow, we'll get the period by dividing the normal period for tangent by the coefficient of x. And we'll get one cycle of the function by setting the argument of the graph between what we used for the normal left and right asymptotes for tangent which were negative pi over 2 to positive pi over 2. So you give me a graph that's been shifted. I'm going to find out how it's been shifted by setting the argument between negative pi over 2 and positive pi over 2. Amplitude doesn't really make sense when you're talking about tangent. It doesn't have a maximum and a minimum height. It looks like x cubed. It goes forever down to forever up. So there's no point in writing amplitude here, but I could say the period of the function is the normal period of tangent, which is pi, divided by the coefficient of x, which in this case is 1. So this graph still has a period of pi. Excuse me, what it has is a shift of pi over 4 units to the left. Since I'm not good at doing that in my head, I'm going to get my left and right asymptotes by setting the argument of that function between the normal asymptotes for tangent, which are negative pi over 2 to positive pi over 2, and solve for x. Just subtract pi over 4 from each side. This is negative 2/4 minus another fourth is negative 3/4. And this is 2/4 minus 1/4 is 1/4 pi. We said the period of this function is pi, so is that the actual distance we have from negative 3/4 pi to positive 1/4 pi? If you subtract those, sure enough, that's a distance of pi units. And to graph this, I'm going to make my tick marks count by quarter pies. Negative 1/4, negative 2/4, negative 3/4 pi to 1/4 pi. That's my left and right asymptote. I know that between its left and right asymptote, tangent has an x-intercept. So halfway between negative 3/4 and 1/4, or negative pi, 3/4 pi, and positive 1/4 pi, I have an x-intercept. And also between its asymptotes, the graph of tangent looks like x cubed. I don't have to find a bunch of points here. I'm just trying to get a rough sketch in my head so that if I punch this on the calculator, I'll know what to be expecting. This is the mental image of what I'm expecting my calculator to give me for the graph of that function. All right, I have 3 more if we can get them done. Number 4, I know that the graph of cotangent looks kind of like tangent, except for it's the reciprocal. Cotangent's the reciprocal of tangent, so where this looks like x cubed, this graph will look like negative x cubed. It'll go downhill from left to right, except what happens to the graph of, say, y equals x squared? That's a concave up parabola. What happens to that graph if I put a negative coefficient on it? Y equals x squared is a concave up parabola. Y equals negative x squared is a concave down parabola. So putting a negative coefficient on a function reflects it with respect to the x-axis. Cotangent normally would be going downhill from left to right, but because of that negative coefficient, this is going to reflect with respect to. I didn't want to write that out, but that's reflect with respect to the x-axis. That means this graph is going to be going uphill from left to right, like tangent does. That's what I'm expecting the graph to look like. Doesn't make sense to talk about amplitude when we're talking about cotangent. So let's find the period of this function by taking the normal period for cotangent. The normal period for cotangent is pi, and divide it by the coefficient of x. This function is going to have a period of pi over 2 rather than a whole pi. And to get the left and right asymptotes for the graph, take that argument and set it between the normal asymptotes for cotangent. Cotangent has its vertical asymptotes at the whole pi's because that's where sine is 0. So we can set that argument between 0 and pi. Note that I have here, set the argument between 0 and pi because that's where cotangent normally has its asymptotes. Solve for x, and you'll see where the asymptotes have been moved to. Add pi over 6 to each side. That's 6, 6 plus one more 6 is 7, 6 pi. And then divide each side of that inequality by 2. Pi over 12 to 7/12 pi. Is that the interval that we expected? Is that a half pi? Well, if you subtract 7/12 minus 1/12, that's 6/12. 6/12 pi is the same as pi over 2. So that's how I check to make sure that I've solved that inequality correctly. The only other thing I need to do, since my units here are counting by 12ths, that's what I'm going to make my tick marks represent. This is 1/12, and then 2, 3, 4, 5, 6, 7/12 pi, and halfway between those would be my x-intercept at pi over 4. 7/12 minus 1/12 is 6/12. Half of 6/12 is 3/12. 3/12 is a fourth. So that's pi over 4. I have my vertical asymptotes at pi over 12 and 7/12 pi. And we've already decided that normally cotangent would go downhill from left to right, but because of that negative coefficient, this graph is going to go uphill from left to right. And that's the quick mental image of what I'm expecting this graph to look like when I punch it on my calculator. All right, cosecant. Doesn't make sense to talk about amplitude because it goes forever up and forever down. But the vertical asymptotes for cosecant are normally at the whole pi's because cosecant's the reciprocal of sine, and that's where sine is 0, the whole pi's. The period of this function, the period of cosecant is normally 2 pi. We divide that by the coefficient of x. We find out this function still has a period of 2 pi. To find one cycle of the graph, I'm going to reword that. Instead of one cycle, I'm going to say left and right asymptotes, because cosecant has a left-right asymptote and then a middle asymptote as well. Just take that argument and set it between the normal endpoints for one period of cosecant. That's 0 and 2 pi. Subtract pi from all three sides. And sure enough, we still have a length of interval from negative pi to 1 pi is a length of 2 pi units. So that period is correct. And if I have left and right asymptotes at negative pi and pi, then halfway between that would be 0. I'm going to have the middle asymptote at x equals 0 or the y-axis. Quick sketch. I have left and right asymptotes from at negative pi and at pi. I have my middle asymptote halfway between those. It's hard to dot in your y-axis. But also, I can remember that cosecant goes up between its left and right asymptote. It goes down between its middle and right asymptote. Try that again. It goes up from its left to its middle asymptote. It goes down from its middle to its right asymptote. Both cosecant and secant have a concave up before it has a concave down if you pick the right interval. One period of cosecant goes from 0 to 2 pi. One period of secant goes from negative pi over 2 to 3/2 pi. So this graph we're working on, normally it would turn around at positive 1 and negative 1. Because of this coefficient, the graph's going to turn around at positive 2 and negative 2. So between the left and the middle asymptotes, it's going to have a concave up that turns around at positive 2. And between the middle and the right asymptotes, it's going to have a concave down that turns around, I was going to say negative 2, but I accidentally, that's going to be hard to fix. It's supposed to turn around at 2, negative 2, not negative 1. The last one, this negative coefficient is going to reflect the graph with respect to the x-axis. That means instead of having the concave up and then the concave down, this function is going to have the concave down and then the concave up. Its period is the normal period for secant, which is 2 pi, divided by the coefficient of x, and 2 pi divided by 1/2 is 4 pi. This graph takes a whole 4 pi units to do both its concave down and its concave up. To see where the asymptotes have been shifted, actually these haven't been shifted. There's no plus something or minus something in the argument. So this graph has its left and right asymptotes at 0 and 4 pi. No, that is not right. Secant has its asymptotes at the 1/2 pi's because that's where cosine is 0. Cosine is 0 at the 1/2 pi's. So I need to say left and right asymptote. Set that argument between what we use for the normal left and right asymptotes for secant, which is negative pi over 2 and 3/2 pi. And then multiply all 3 sides by 2 to find out where that left and right asymptote are. The left and right asymptotes are at negative pi and 3 pi. Is that a distance of 4 pi like we predicted? Yes, from negative pi to 3 pi is 4 pi radians. here's negative pi, and then 1, 2, 3 pi. That's my left and right asymptotes. Halfway between negative pi and 3 pi is my middle asymptote. And I know that because of the reflection, this graph has its concave down part before its concave up part. So halfway between negative pi and pi, you have concave down piece that turns around at -1. Halfway between pi and 3 pi, you have your concave up piece that turns around at +1. All right, I really hope this was just review for you because in pre-calculus, I got to spend about 3 days on this, and to review, we only had an hour, but you can watch the video again if you need to. You can pause the video if you need to. That's the great thing about watching the lectures on video. Your homework tonight is from the appendix D.3, and I think I retyped those problems for you on a separate page. I have these problems for tonight's homework on a separate page, and then I have the answers to the homework following that page. So good luck, and I will see you tomorrow. We'll answer any questions from the homework, and we're just about reviewing. You ready for calculus?